In this video, we'll discuss the technical aspects of the machine learning models used for neural machine translation. But before we start, I'd like to point out that you don't need to understand or memorize the technical or mathematical details of these models to use them effectively for your purposes. The purpose of this video is to give you enough of the technical background to build an intuition for why certain behavior might arise when you're using the models, and why one model or one decision may be more appropriate in a particular circumstance than another. On this slide, I've provided a list of concepts you should understand at an abstract level by the end of the video. These might not make a lot of sense now, but when you're reviewing, you can use this list to double check that you're on the right track. Now, when you have really limited data, it's still probably preferable to fall back on one of the earlier translation techniques that don't involve neural networks. Lookup tables directly map tokens from the input sequence to tokens in the output sequence. For example, a bilingual dictionary can be used to translate a sentence word for word into a different language. However, this approach misses important parts of translation, such as differences in grammar, struggles with unknown or misspelled inputs, and can't be applied to many transduction tasks. Statistical methods are a step up from this. Often we phrase the situation as trying to find the output sequence y star, which maximizes the probability that y is the correct output sequence, given that x was the input. Often it's easier to model that probability, the probability that x is a reasonable input given that y was the correct output, and also the probability of y under some language model. So we reverse the problem using Bayes' rule and model these two probabilities through techniques such as n-gram language modeling, hidden Markov models, or Gaussian mixture hidden Markov models. Though we won't use these techniques for translation in this course, these techniques are still used for some very low resource sequence transduction tasks. ELPIS, which you saw in Module 2, uses these sorts of techniques for transcription for low-resource languages. However, there's an upper bound on the sorts of performance that you can get from these techniques, and newer neural methods have raised our expectations for these technologies beyond this bound. Neural machine translation refers to machine translation that is approached using neural networks, or a deep learning approach to machine translation. Hopefully most of you have seen a basic neural network before, but if you haven't, they're generally represented like this. The most common network type is a feed-forward neural network, in which you might have some numbers for the input and one or more hidden layers. These hidden layers take a weighted sum of their inputs with a bias offset, and then feed this through a nonlinear activation function. The result is an output from that neuron, and uses input to other neurons. The problem of training a neural network is basically the problem of figuring out what these weights should be by showing the network lots of examples of correct input-output pairs and trying to figure out how to reduce the error between the network's guesses for the outputs and the actual output seen in the data. However, these simple networks have a hard time with sequences. Say we have a ball in a box and we want to predict where it will be next. Given this image, where would you think that ball should move to next? Any guess would pretty much be at random. However, if we add context of where the ball has been in the previous time steps, we can make a better and more informed guess at what will happen next in the sequence. To predict what will happen next, often we need to understand what's already happened, and with sequences, often we need an understanding of the order in which that history has occurred. This is where traditional feed-forward neural networks trip up a little. Each layer in a feed-forward network takes inputs from the previous layer and feeds to the next. So if you put in the same inputs over and over again, you'll get the same output over and over again. That is, feed-forward networks have no concept of memory, so they don't handle sequences very well. Recurrent neural networks were created in an attempt to handle sequential data. The output depends not only on the input, but also on the previous state of the network. Often you might see these networks unrolled through time like this, so they start to look like a feed-forward network, but where the weight matrices from input to hidden to output, and current time step to next time step remain consistent across time steps. These networks, when unrolled through time, can get very deep, and so fall victim to the exploding or vanishing gradient problem. This problem essentially happens when many layers with certain activation functions are added, causing the gradient of the loss function to become very small or very large and making the network hard to train. This means that recurrent networks can struggle with long sequences and long-term dependencies within sequences. So to try to counteract this, certain network structures have been introduced which gate what's led into and out of certain cell states. The most popular variant is called the long short-term memory network, or LSTM, However, gated recurrent units or GRUs are simpler, can be trained with less data, and perform similarly to LSTMs as long as the sequences aren't too long. So, RNNs help us process sequential data, but for sequence transduction, we often use them in an encoder-decoder framework. In the context of NMT, the inputs and outputs here will usually be a sequence of vectors, which are either one-hot encodings or word or token embeddings. The most basic recurrent encoder-decoder encodes the entire input sequence into a fixed-length context vector using a recurrent neural network before decoding from that context vector without being able to refer back to the original input. The length of the context vector has to be determined ahead of time, which can limit the power of the model. Additionally, memorizing an entire sequence into a static vector which contains its entire meaning, and then having to decode without ever referring back to the input, isn't an intuitive way to approach sequence transduction. Realistically, when we transduce sequences, we pay more attention to specific parts of the input at specific points in the decoding process. For instance, in translation, there will be words in an input sentence that should have more or less impact, depending on which of the words we're decoding at any given time step. A lot of the time, the order of the input might already align with the order of the output. However, if this was always the case, lookup tables would be sufficient for sequence transduction. For translation, differences in grammar and word order can throw off the alignment between source and target sentences. So a major challenge in sequence transduction is finding how tokens in an input sentence or sequence align with tokens in an output sequence, to figure out how much attention to pay to specific parts of the input at each stage of output generation. By figuring this out, we can weight contributions from each input more strategically at each time step. So the model shown is the current standard for recurrent sequence transduction. This model uses a bidirectional recurrent encoder where each HI represents the same recurrent unit across time steps. One network reads sequences left to right, while the other reads them right to left. The decoder now features an attention mechanism, which frees the network from fixed-length compression, instead weighting each input as it sees fit according to learned attention weights as per the equations on the right. After constructing a new context vector from a weighted sum of the inputs, a unidirectional recurrent network decodes. Transformers represent the new state-of-the-art when it comes to many sequence transduction tasks. At each step, they're autoregressive, but not recurrent, so information about what's happened in the past is fed directly to the network, rather than remembered through some hidden state. Because of this, they can be easily parallelized within sequences and aren't as deep as recurrent networks, which helps them to avoid some of the problems mentioned earlier. The transformer still uses an encoder-decoder framework. The entire input sentence is fed in at the input to the encoder, and because the whole input is fed in at once, the network would have no idea about the order of the words. So positional encodings are added to the input word embeddings. These can be learned as part of the network, but often they're calculated ahead of time. The key to this model are these multi-head attention mechanisms, as well as something called self-attention. The multi-head attention mechanisms are made up of multiple heads, where each head is an attention mechanism applied to a different linear projection of the sequence. By linearly projecting the sequences into various different spaces using learned parameter matrices, and applying attention in each of those spaces, we can draw out different interesting features of the sequence. So for instance, the network might have one head that learns to pay attention to who a sentence is about, and one that learns to pay attention to where the sentence takes place. The multi-head attention mechanism in the encoder and the masked multi-head attention mechanism in the decoder applies self-attention to the input sequence and the previous outputs from the target or hypothesized sequences, respectively. The network then uses this information to map the current concept of interest from the input representation to the output representation. When decoding, the network looks at both the output from the encoder blocks and the previous outputs generated by the network. In training, it's common to use the actual target rather than the previously generated outputs, but when using the trained network, we no longer have access to these. So the masked multi-head attention mechanism masks all positions after the current position of interest during training. You might also notice that there are a few residual connections throughout the network, which help to propagate positional information further into the network.